Ever look at a ridiculously complex physical system and just think, nope, absolutely not. The math on this is going to be a total nightmare. Well, you're definitely not alone. Sometimes physics can really feel like hitting a mathematical brick wall. But today, in this explainer, we're literally unlocking the ultimate physics cheat code. We're going to see how a simple, almost elegant shift in perspective can take the absolute messiest, most chaotic scenarios you can imagine and boil them down to incredibly simple solutions. Let's dive in. So to really grasp why this cheat code is a complete game changer, I want you to picture an artillery shell. It's fired into the air, traveling in this massive, perfect arc high across the sky. Now, imagine that shell suddenly exploding midair. Boom! Suddenly, you're no longer looking at one distinct, gracefully moving object. You've got thousands of jagged fragments violently scattering in literally every direction. Some are rocketing upward, some are careening down, spinning, colliding. If you were the scientist tasked with tracking that entire system's trajectory, measuring the exact vector forces of every single piece, how on earth do you even begin to track all that? Well, spoiler alert, you don't. Actually, scratch that, you can't. Trying to calculate the individual paths, masses, and velocities of a million chaotic fragments would completely break you. You'd need a massive supercomputer for that. So instead, you track a single, invisible, imaginary dot. We call it the center of mass. By shifting our perspective totally away from the physical, noisy fragments and focusing strictly on this one ghost-like point, the impossible math suddenly becomes, well, incredibly simple. And that brings us right to the formal definition, the theorem on the motion of the center of mass. It tells us that this specific point moves exactly as if all the mass of the entire system were concentrated right there, and all external forces were applied directly to it. This right here, this is the actual cheat code. What it proves mathematically is that internal forces, like that massive, violent, explosive force pushing all those shell fragments apart, have absolutely zero effect on the acceleration of the system's overall center of mass. None. Let's break that down just a bit more by looking at the forces at play. On one side, you've got your internal forces. The explosion is this huge internal force, creating a totally unpredictable scatter. But because of Newton's third law, every action has an equal and opposite reaction, all of those internal explosive forces cancel each other out perfectly when you look at the system as a whole. On the flip side, you have external forces. Gravity is an external force, continuously pulling down on the entire system from the outside. Because those internal forces essentially delete themselves mathematically, gravity becomes the absolute only thing that dictates the path of our center of mass. The result? A serene, perfect, parabolic trajectory, completely unbothered by the sheer chaos happening around it. I honestly love to think of the center of mass as kind of like an invisible understudy. Imagine you're watching this deeply dramatic play, right? Suddenly, the lead actor spontaneously combusts, and the supporting cast starts flying all over the stage in pure, unscripted panic. The invisible understudy doesn't even flinch. They just smoothly stroll right across the stage, hitting every single mark, continuing the performance exactly as planned, totally ignoring the mayhem. That's your center of mass. Okay, so how do we actually visualize the math behind this understudy? Look at this representation. Whether you're dealing with something super simple, like a dumbbell, just two masses on a stick, or a ridiculously complex system of scattered particles in 3D space, the center of mass is just the exact balancing point. Think of it like this. If you could somehow rest that entire, perfectly connected system on the very tip of a pencil, that dot is the exact spot where it would balance perfectly without tipping over. Now, please don't let these giant sigma equations intimidate you. When it comes time to actually calculate where this point is, the formula is surprisingly intuitive. If you look closely at the equation for the x-coordinate, all we're really doing here is finding a weighted average of the mass along the x-axis. That's it. You just take each individual piece of mass, multiply it by its x position, add up all those numbers, and divide by the total mass of the whole system. Boom! That gives you the exact x-coordinate of your balancing point. And as you'd probably guess, we apply the exact same weighted average logic to the y-axis. We just swap in the vertical positions and run that identical, straightforward average. By combining those x and y coordinates, we are pinpointing that one imaginary balancing dot on a 2D grid. It's just a highly elegant, super clean way to collapse a messy physical reality into one single, totally manageable mathematical coordinate. All right, let's take this to the next level and see how this builds when objects actually smash into each other. Because understanding the center of mass actually opens the door to another incredibly powerful concept in physics: momentum. When you have two moving bodies colliding, Tracking the center of mass becomes the ultimate master key to unlocking exactly what's going to happen next. But before we start crashing things together, we've got to establish an absolute golden rule: the conservation of momentum. It simply states that in a closed system, meaning a perfectly contained bubble where no outside forces like friction or some random external push are interfering, the total momentum right before collision perfectly equals the total momentum right after. Again, thanks to Newton's third law, the forces these objects exert on each other during the crash are entirely internal. They cancel out. Therefore, the total momentum of the system is permanently locked in. It's our ultimate mathematical anchor. Now, even though momentum is always locked in, the specific type of crash can vary pretty wildly. Physicists generally break these down into two main categories, which you can see diagrammed here. You've got elastic collisions, where objects smack into each other and violently bounce off. And then you have inelastic collisions, where objects hit, crumple up, and actually stick together, moving as one big merged mass afterward. The real secret difference between these two isn't just the bouncing versus the sticking, it's what happens to the energy. In a perfectly elastic collision, kinetic energy is fully saved. Think of two incredibly smooth billiard balls clicking together and immediately rolling away. But in perfectly inelastic collisions, like two heavy balls of wet clay slamming into each other, kinetic energy is lost. It rapidly transforms into heat, a loud slapping sound, and the physical deformation of the clay itself. But here's the crucial part. Even though that energy is lost to heat and sound, our anchor remains. Momentum always survives. So let's look at a classic real-world application of a perfectly inelastic collision, the ballistic pendulum. Imagine you're an engineer in the 1700s, and you need to figure out the exact speed of a bullet. You have no high-speed cameras, no lasers, no radar guns. How do you possibly measure something that small moving that unbelievably fast? Well, they used this incredibly simple device to figure it out, relying entirely on the exact physics cheat codes we're talking about today. So how does this genius little apparatus actually work? You fire a bullet directly into a heavy, stationary block of wood hanging from some strings. The bullet embeds completely deep into the wood. There's your perfectly inelastic collision. A massive amount of kinetic energy is totally lost in a fraction of a split second, but momentum is perfectly conserved. The newly combined block and bullet mass then swings smoothly upward together, acting just like a pendulum. And here is the truly genius part. By just taking out a ruler and measuring the final height of that swing, we can work backward using our momentum cheat code to calculate the bullet's exact initial speed. I mean, that is just brilliant historical detective work. Okay, let's apply this to a wildly fun multi-body problem pulled straight from an MIT physics problem set. Picture this. An acrobat jumps straight upward off a trampoline. Midair, at the absolute gravity-defying peak of his jump, he reaches out and violently grabs a clown who is just casually hanging from a trapeze above him. We need to find the maximum height the acrobat and clown reach together. Trying to track their individual colliding bodies, their flailing arms, those giant clown shoes, it would be practically impossible. To solve this, we just break this chaotic circus act down into 3 clean, distinct steps, almost like a sports commentator breaking down a slow-motion replay. Step 1. The acrobat's initial upward jump, which gives us our starting momentum. Step 2. The exact moment the acrobat grabs the clown. Because they move together immediately after, this is our perfectly inelastic collision. Step 3. The newly merged mass, acrobat plus clown, moves smoothly upward to its new final peak height. By using our center of mass cheat code, we know this entire messy system continues completely predictably. The upward momentum the acrobat had right before the grab has to perfectly equal the momentum of the combined masses right after the grab. We literally just set the initial momentum equal to the new, heavier combined mass multiplied by their new velocity. By totally ignoring the flailing limbs and focusing purely on the center of mass, we effortlessly calculate the new speed of that merged acrobat clown unit. And from there, finding their final height is an absolute breeze. And honestly, this brings us to why all of this genuinely matters. Treating a complex, messy, totally chaotic system as a single point mass saves us from absolute mathematical nightmares. It fundamentally does not matter if it's a violently exploding artillery shell, a speeding bullet tearing into a block of wood, or an acrobat bear-hugging a clown mid-air. The underlying, beautiful principle remains exactly the same. By strictly ignoring all that internal chaos, the blistering heat of an explosion, the deafening sound of a crash, the violent fragmentation, the awkward mid-air grabbing,
and focusing strictly on the external forces, like gravity. This invisible center of mass just simplifies the entire universe. It lets us gaze right into the future of a system and mathematically predict its exact outcome, even when the present moment looks like complete and utter disorder.
It really leaves you wondering, doesn't it? If a simple shift in perspective, just zooming out from a million chaotic fragments to focus on a single serene imaginary point, can completely solve the impossible in physics, where else could we apply this ultimate cheat code? What other deeply complex, incredibly noisy problems in science, or hey, even in our daily lives, are just waiting for us to find their center of mass? Thanks for joining me on this explainer. Keep shifting your perspective, and I'll catch you on the next one.